Okie doke, so, okay, working right, everyone can see the screen, okay. So today is going to be the last official lecture, except for tomorrow. Tomorrow we'll have Dr. Roberts here, so please come to that if you can. Today, thank you for trying to be helpful. Today I want to talk about CMake. And CMake is a type of build system. So basically when your project gets really large or when it could be built on different systems. So say for instance, even working on your projects on your computer and then moving them to CHPC, you have to do different things. You have to load modules on CHPC where you don't have to on your computer. A build system becomes extremely helpful because a build system figures out your environment. It figures out what compilers you have, it figures out what flags you need, it figures out how to link stuff together, so you don't have to do all of that stuff. So Make, what we've been using, so Make files, that is a build system. It does build your project for you, so you don't have to manually type compiler, flags, do this on this file and do it 1,000 times. So it is a build system, but you have to specify everything by hand, like your compilers and your flags. Whereas a meta build system, as they're sometimes called, do all that for you. So, for instance, Microsoft Visual Studio has its own build system in the form of project files. You make a project, you put your files in it, and you tell it what libraries you need, and it goes ahead and figures out how to compile it. Okay. So those of you who have used Visual Studio have seen that. Now the granddaddy for Linux is called autoconf. Stands for autoconfigure. It's basically a glorified shell script. And I've looked at some of these shell scripts. They're like 10,000 lines long. Very complicated. You know a project is using it if the install instructions say to do configure, make, and then make install. And it's the configure that gives that away. So the configure script, it's a shell script. Again, it's 10,000 lines long. It goes and figures out what compilers you have and what flags you need and all this other stuff. And it actually makes a make file. And then you type make, so make then runs and compiles everything. And then make install actually installs it to a special location on your computer so you can use it. A lot of people find it to be arcane, very difficult to use, fragile, brittle, breaks easily, kind of thing. And there have been people who have tried to make replacements. And so one of these replacements, and it's a really big one, it's used all over the place, is called CMake. Open source project run by a company called Kitware. CMake itself is free, but the tutorials are not. They have a book called Mastering CMake that you can buy for $50 off by Amazon. You can go to their special seminars and pay hundreds of dollars for those. Anyway, so they give you a system and don't tell you how to use it. So, however, the official documentation is available online. And then there's lots of questions on Stack Overflow with good answers, and there's a few okay tutorials on random blogs. So it's used by a lot of large projects. Netflix uses it, KDE uses it, and one KDE developer said this, that CMake doesn't make you want to shoot yourself with a nail gun when building your project anymore. So, and the KDE guys, they're good. They're the guys that started the IGN project. They're the guys that run Kubuntu. Anyway, so they know what they're talking about. They're good. They're really good programmers. So CMake itself uses a scripting language. So it's another language. Of course, it's always another language. And you use this language to describe your project, and then CMake figures out how to build the project. So just like the configure script, what it does is it makes a makefile, and then you can use make to compile your project. If you're on Windows, it creates Visual Studio files instead. So it tells Visual Studio how to build your project, which is really handy. They try to make it cross-platform, so it works wherever you want to use it. So instead of a make file, you use these CMake lists.txt files. I don't know where they got that name from, but that's what it is. And this is the end of the slides because I'm just going to show you stuff from here on out. But there's a few basic types. I want to say first, I'm not an expert at this. Okay, I've never read the Mastering CMake book. I looked; the library doesn't have it. I've just kind of pieced things together, and I haven't found a decent tutorial either. But there's a few basic types. You have variables. And CMake comes with dozens, hundreds of global variables. So all the default CMake variables are in all caps, and all variables are strings. Okay, there's no numbers, there's no characters, there's no nothing. It's just text, straight text. Oftentimes using CMake then is a game of find the right variable, and you can of course make your own for your own purposes. And I'll show you examples of that. Functions. There are a lot of functions in CMake. Often it's a game of find the right function to combine with the right variable as well. The functions themselves are case sensitive, so you can write them however you want, and then it'll figure it out. Targets. So targets are very much the same idea as a make target. These are the things that will get built. So these could be libraries, it could be executables. And then properties. Every source file or target has a large list of possible properties associated with it, which you can then set on an individual basis. Okay, so time for the examples. Go ahead and blow this up. We'll turn the light off so you can see. Which one? This one. Okay, first let me do this stuff. Okay, so just going to get rid of all this. Okay, so now it's clean. All we've got is this hello world C++ file and then the CMake list.txt file. So this is the simplest project you're ever going to see. Okay, so there's a few requirements. So you have to have this line here. CMake minimum required. What that's referring to is the version of CMake that you're using. Because CMake does change from version to version. They add things, they delete things. Mostly just add things. They don't ever delete anything, I don't think. And so that way it knows that when you're running CMake, so if we type CMake -- version, it'll tell me this is 2.8.12.2. Okay, and so I have to be using at least version 2.8. I could change this to 1, and then I could use an older version. But you have to have this. It has to be like the first line or something. And then you tell it this is going to be a project. It's going to be called hello. It's the name of the project. And we're going to add an executable. So all these three are functions. Okay, and so we add an executable, it's going to be called hello world, all right? And it is dependent on hello world.c++, okay? So And that's it. That is literally all you have to type. So now we type CMake and we tell it where to find the CMake list file. Okay, so I have a dot saying it's in this directory. Alright, so you'll see what it's doing is it's looking for a C compiler, which it found, a C++ compiler, which it found, okay, and some other stuff, and then it says configuring done, generating done, it wrote build files. So if you type ls, you'll see here we now have a bunch of other files. The most important one for you, most important to you, first off is the make file, and then the cache file. So if you look in the cache file, this actually holds, it stores a bunch of values that got set while it was configuring everything. And you usually don't have to care about most of these, okay? Because every single one of these is a variable that you could have modified, or something could have modified. So, anyway, you generally don't have to worry about most of this. So then we type make, okay? And you see it gives you nice color output. Isn't that cool? It's all in color and it says built target hello world. So if we look here, we see, hey look, we have a hello world, which we can actually run. Okay, I don't actually remember what this is doing. Oh, it really was that big. Okay. All right, so you can see how easy that is. However, there's one thing that annoys me. I don't know if it annoys you, but it annoys me. Now we got all this extra junk in here. Make file, CMake install, this folder. I don't even know what this is. Holds a bunch of junk, apparently. Okay. And that's annoying, to say the least. So we can do a make clean, but that doesn't get rid of all of them. All it does is get rid of the hello world. Which means we have to manually go through and get rid of all this stuff. Let's go to cache. Okay, so that's annoying. But that's because CMake generates all this extra stuff that it uses, what they generally suggest is you do what's called an out-of-source build. And so you make yourself a build directory, you go into it and you type CMake, but then we'd say the CMake list file is in the directory above. Okay? And now, if we look, our source directory is still clean. And our build directory is where now it puts all of that junk. Okay? In here now we type make, it makes, and we say, okay, where's our executable? Our executable is actually in the build directory. And there are ways to change that. So, but now we can run our executable. It keeps your source separated from your compiled files. And so if you really need to clean up stuff, all you have to do now is that. And it clears out everything. So that's really handy. All right, so that's, of course, a very simple case. So let's look at now pi. Let me make sure we are, okay, we're at initial. So here we have the same thing, except there's going to be some problems with this, I'll show you. So here we have my pi.exec dependent on main. Okay, so we're going to make our build directory, and then we're going to type CMake ... and we type make. Oh dear. Problem. It says this file requires, this is a compiler error. It's saying we need C++ 11, which we have not specified. So the question is, how do we do that? We haven't pulled in any flags or anything. So, oops, I think it's messed up. Oh, I'm in the wrong place. CMake looks okay. All right, so this is how you do that. There is a variable called CMake underscore CXX flags. And whatever language you're using, you can supply in here. So if you're doing Fortran, you can put that in there. And so we're using the set function. The set function actually creates a variable. And then we tell it, in quotation marks, all the flags that we want this variable to have. And you'll notice here, I'm referencing the CMake CXX flags. And the reason being is that CMake will sometimes put its own flags in. And if you don't specify this right here, then you'll be overwriting those. So if I deleted this, that would overwrite whatever CMake had already put into that variable, which is not correct. So we're going to append them by using this $sign and then the curly braces. What that does is actually puts the value that's stored in that variable, puts it in there. And so we append the standard C++11, and in this case, we also need OpenMP. So now, here's another good thing. CMake keeps track of, if you change this file, it will automatically rebuild it. Or regenerate the make file to make sure you do things. And you see now it's compiled. So that's how you can put flags in there. Now here's a question. What if we wanted to use the Intel compiler instead? The problem is the Intel compiler, I think it's something like that. I don't remember. But if you want to use OpenMP, it has a different flag. It has -OpenMP rather than -F OpenMP. So how do we account for this? And CMake comes with what's known as a function called find package. And it comes pre-installed with default, hundreds of default, what's known as find package files, which try to figure out where that package is. And so let's look at step 2. So you see, here I've added this line right here. I tell it find package OpenMP, and I'm going to give it this option that says that it is required. You have to find this, and if you don't, it'll error out. Okay. The other thing that I'm doing, when it successfully finds OpenMP, it creates a new variable called OpenMP CXX flags. And so I'm going to take that and append it now to the CMake CXX flags variable. Okay. So you'll see now it's going to try and detect the OpenMP flag and figure out what it needs to use. And it says eventually found OpenMP -F OpenMP. And it writes new build files, and then it builds our target. Of course, the target already exists, so there we go. Now we know for sure it worked. Okay, so that's the find package, and I'll show you some more advanced usages of that here in just a second. Some water. So what about, say, MPI? We need to find MPI. Now the way we do it is we type MPI CXX. We use that as our actual compiler. And CMake doesn't do that. And the reason being is this, is that the MPI CXX, all it does is call G++ and it sticks on some extra argument flags, some extra flags on the end, telling it where to find the MPI libraries and where to find the include files. And so what CMake does is it actually does that manually. So if we look at MPI here, I'm going to show you an example of this. So here we're going to use find package. We're going to find MPI, and this is required. We add our executable, which is dependent on hello.cpp. And then we have another function called include directories. Now, this is a global function. It sets the include directories for the entire project. If you want it to do it on a target by target basis, you have to modify the properties of that target. Okay. But you say, when it finds the MPI package, it'll set this variable, the MPI include path. And so we use the include directories function to add those directories. And then, here's another function. So we've made a target called MPI. It's an executable file. And we tell CMake, I need you to link the MPI target with the MPI libraries. This is another variable that's set by the find package command. Okay. And then here's an example of setting a target's properties. Let's say we wanted this to show up we wanted the executable to not be in the build directory, but in the source directory, or any other directory for that matter. We can set the target properties. So this is our target. We're setting the property, which is called the runtime output directory, and we call the MPI source directory. So this little MPI, this is the name of our project. And this particular variable gets set when you call CMake, and it's the location of the CMake list file that you use. So we go into our build. Actually, let's do this. We'll clean up our mess here. Make a new one. All right. So now CMake goes through and it finds the MPI libraries. Okay, so they did that there, and then we can type make. Now, what if we wanted to see exactly what commands were being called? So if we wanted to see that, you type make and you say verbose equals true. And now it's actually going to spit out the actual commands that are being used. So here the command is calling C++. It has now the include directory for the MPI library. Okay. It has an output file, okay, and it tells us that we're compiling this particular file, hello.cpp. And then we're going to link this all together. And let's see, the linker command is here. So we're using G++ again as the linker. And we're linking this .o file to, and we're turning that into an MPI executable, and then it adds all these linker commands. You see we have MPI CXX in the MPI library, and it does all that for us. Okay. So if you're having problems with it, you can use the verbose command to try and see exactly what it's doing. And then if we look, there's our executable in the source directory, like we told it, and we can actually run it. And we can run it using MPI run, just like that. Just same as always. Okay. Now, another big thing. What about optimization flags? Because every compiler has different optimization flags. And there's actually, CMake has a standard way of doing this, and that's called build types. And so the way this works, when we run CMake, let's just make clean this, and then actually take that back. Let's just do this. Remove the build directory. Let's make one called debug. And make another one called release. So in the debug directory, we're going to type CMake, and we're going to say -d, which stands for define, and then CMake build type equals debug, and then we tell it ... Okay, it goes through, figures everything out. And if we type make with the verbosity on, is that even a word?
Sure.
Yeah. Okay, you'll notice now it's throwing in a -g flag because we told it we want a debug build, and it knows what needs to be done for a debug build.
What did you tell it was a debug build? Just the fact that it was a debug folder? Or?
No, right here. So
okay.
there's a variable, global variable called CMake build type.
Got it.
Okay, and if we look in the cache file here, you'll see that this variable is the second thing in the CMake cache file. And you can actually change this. So we can change this to release mode. We type make, it recognizes that something's changed in your cache file. And so let's do clean this. Let's do this with the verbose this on. Now we have a -03 flag. So there's generally when you're building a project, you have debug mode where you want to be able to step through it nicely and figure things out. But release mode, you want it to go as fast as possible because that's what you're releasing to the public. You're not testing it anymore. You're just running it. So you want it to go as fast as possible. And then there's also a third option. If you look in here, it actually gives you the 4 options that you can use. Debug, release, release with debug info, so that compiles with the -g flag. And then the minimum size release, which tries to make your executable as small as possible, using the appropriate flags. But the beauty about this is that we can have a debug version and a release version running at the same time by keeping them in 2 separate folders. And so you can run the release one, you can change some stuff in your code, recompile the release, see if it works. If it doesn't work, then you can recompile the debug one and use that one to figure out what's going on. Okay. Otherwise, you'd have to make clean the entire thing, change your flags in your make file, and recompile the entire thing in order to get that working. So, now I want to show you how we deal with larger ones. We're almost done here. So this is my dissertation project. CMake has made this so much better than what it used to be, where we just had make files. And so this is my main CMake list. Okay, it's actually not that long. And the only reason it looks so nasty is because I have to do a couple things by hand. So, for instance, very first thing I do, I just throw C++ 11 in there. Okay, I just need it, so I just throw it in there. And now I have some very specific Fortran flags that I need. But sometimes I'm using the Intel compiler if I'm on CHPC, and other times I'm using G++ on my own computer, and so the flags are completely different. And so there's a variable called the CMake language compiler ID. And I say if that's equal to Intel, then I want to add these flags. Or else if it's equal to GNU, then I want to use these flags. Or else print out a fatal error message. Okay, because it only works for those two. And I could make it more robust, but no one else is going to be using this, so who cares? But the thing is, now I don't have to go and manually change the flags. CMake figures it out for me. Add definitions, so these are defines that you want to add. Adding subdirectories, so you can actually have hierarchies of CMake list files. Each one of these directories has its own CMake list file. And so then I tell it I want MPI. Here I'm setting up my executable files, okay, and things that need to link to them. So let's go ahead and look at Cart3D CMake list. So this is Cart3D in my Cartesian solver. Yeah, I need to find the Samurai libraries, and then I can include those. And I can link all the Samurai libraries up here. And these are finding the include directories that are necessary. This is for Boost on CHPC. It's the only way I can figure out how to get it to find Boost. So this is basically what this is doing. This is setting up this library. I have a library called Cart3D. It's going to be a static library, and it's dependent on these files. Now these files come from some other CMake lists. And so let's go look at those. So in here, I'm setting a variable called numerics files, and it's going to include all of these files. So now CMake knows that it needs to compile these files. So we're going back up the tree here to the top level CMake list file. And at the top level here, I'm telling it I have an executable Cart3D. It's dependent on this main.c file. Okay? And I'm linking in the Cart3D library, and the physics library, and the utilities library, and the MPI libraries. And those are all contained in these subdirectories that I've added here. So let me show you an example how this actually, so we go into the build directory, and it's just going to be clean. I'm going to show you the coolest part about this. It gives you a nice little counter, tells you how much it's done. So right now it's compiling the physics library. It compiles each one of these files and then links them all together into a static library. And now it's doing the Cart3D library. Okay? But that's really slow. So let's run it in parallel, shall we? This makes things go really fast.
That's awesome.
And that's done with the -J flag. Okay, so you type make -J and then the number of processors you want to use. And you can see why we need a build system for a project this big. It's just ridiculous to try and maintain it on your own. So, like I said, I'm not an expert at CMake. I've just shown you the basics. This is stuff that I've managed to piece together off the internet. And it works well enough. So it scales from the smallest projects to the biggest projects. It's absolutely fantastic. It gives you nice colors. We thought colors would be amazing, but it is.
The red kind of freaks me out though. It looks like you did something wrong.
It's not red, it's pink. It's true though. But now it's linking together. So it finished making all the all the libraries and links together all the executables. And so by doing so, here's the other cool thing. Using make files, it can be really hard to track dependencies on header files. CMake actually reads your code and says, okay, so this includes this and this includes this. So if I change one of those files, for instance, let's see here. Let's do numerics. Okay, so I'm just going to change this file. And then if I go back to the build directory and type make, it knows that all of these .c files include that .h file. All I've told it about is the .c files. I never told it about .h files, but it knows that because they are dependent on the .h file, it needs to recompile these. You can't do that with make by itself. With Fortran files, it will read them and find the use module statements and compile them in the correct order. So you don't actually have to worry about that anymore. With Fortran, you always had to worry about that. Because if you didn't compile them in the right order, it didn't work. Obviously, it takes a long time, so we'll make it go faster. So it also knows that the strand Cartesian interface manager depends on that file, so it recompiles that as well, which is super handy. And it did that without having to recompile the strand code, because the strand code is not dependent on that .h file. So anyway, so that's my very short, very incomplete tutorial on CMake. I'm not an expert, but I'm trying to be, I guess, without paying for it.
Yeah.
So anyway, that's all I have for you today. This is the last lecture other than tomorrow. So I hope everyone has a good rest of the summer. Sorry I ruined everyone's summer, but I hope you learned something useful. And I hope this will make you a better programmer. You may never use it again, but it's cool. You can say you took a class on using a supercomputer, right?
It's true.
So, anyway.
I can't.
Yeah, you didn't take a class. You just showed up.
I just
And anyway, so have a good summer. We'll see everyone in the fall again, I guess. Or we won't, either way.